Section: Introduction. In this section, we discuss how large language models, LLMs, built on the transformer architecture have become essential for many advanced AI systems, such as GPT-3, GPT-4, Gemini, and Llama. We note that the impressive advancements in these models are guided by neural scaling laws, which show a power-law relationship between training loss, the number of model parameters, and the amount of training data. A crucial takeaway is that optimal performance is not just about increasing model size. It requires scaling both the number of parameters and the training data together. For instance, the Chinchilla model, with 70 billion parameters, outperforms the larger Gopher model, which has 280 billion parameters, because it was trained on 4 times more data. This highlights the importance of data scaling alongside model scaling for better performance in LLMs. As AI progresses, we face a challenge in obtaining high-quality tokens. Therefore, we need to explore new methods and architectures that can scale more efficiently than traditional transformers when token availability is limited. However, we find that most improvements in architecture and optimization merely shift errors without significantly altering the scaling laws. Previous studies indicate that most architectural changes do not affect the scaling exponent, and similar findings apply to optimizers. The only positive change has been related to data distribution, which can influence the scaling law's exponent. In this context, we revisit earlier work that generalizes the dot product attention of transformers to trilinear forms, introducing the two-simplicial transformer. We investigate generalizations of rope to trilinear functions and present a rotation-invariant trilinear form that we prove is as expressive as two-simplicial attention. Our results show that the two-simplicial transformer scales better than the standard transformer under limited token budgets, outperforming it in math, coding, and reasoning tasks. Additionally, we discover that the two-simplicial transformer has a more favorable scaling exponent in relation to the number of parameters, suggesting that we can increase tokens at a slower rate than parameters for this model. Our findings imply that, under token constraints, the two-simplicial transformer can more effectively approach the inherent complexity of natural language compared to traditional dot product attention transformers. We also review related work on attention generalizations since the original transformer. Many efforts have aimed to reduce the quadratic complexity of attention with longer sequences. For example, local attention has been used in image generation and language modeling. Some researchers have proposed alternatives to softmax attention, showing that using an exponential function without normalization can lead to linear time transformers. However, linear time attention methods, like state space models, have not been widely adopted due to their lower quality compared to transformers. On the other hand, some work has focused on higher-order attention, such as the two-simplicial attention, which has been shown to be effective for logical problems in deep reinforcement learning. Other models, like the edge transformer, have introduced triangular attention mechanisms. The AlphaFold paper also utilized a similar attention mechanism based on the geometry of proteins. Recent studies indicate that the two-simplicial transformer can solve a broader class of problems than dot product attention transformers, particularly in complex reasoning tasks. We acknowledge that while higher-order attention and looping mechanisms aim to compute more expressive functions per parameter, scaling loop transformers presents challenges in training. Specifically, increasing the depth of these models can complicate training, and further research is necessary to address these issues. Section Summary. In this section, we discuss the significance of scaling both model parameters and training data for optimal performance in large language models, highlighting the advantages of the two-simplicial transformer over traditional transformers under token constraints. We also review various advancements in attention mechanisms, emphasizing the potential of higher-order attention to enhance expressiveness and efficiency in AI applications. Section: Notation. In this section, we use specific notation to clarify our discussion. We represent vectors with small bold letters, matrices and tensors with capital letters, and scalars with small letters. The dot product between two vectors, denoted as A dot B, is represented by the notation A, B. For the trilinear dot product, we express it as the sum of the products of corresponding elements from three vectors. We use the at symbol to indicate matrix multiplication, such as when we write AB at C. For matrices A, B, and C, when we slice arrays, we denote it as A, L, L plus M, which means we take elements from index L to L plus M minus 1, using zero-based indexing. Some tensor operations are described using Einstein summation notation, similar to what is found in the NumPy library. We refer to floating point operations as flops. When we stack arrays in columns, we write them as A, B, C. The determinant of a square matrix is denoted as det. Next, we provide a brief overview of neural scaling laws. We follow the approach that suggests the loss, denoted as L, N, D, decreases according to a power law based on the total number of model parameters N and the number of tokens D. The first term, E, represents the irreducible loss related to the entropy of natural text. The second term reflects that a model with n parameters does not perform as well as this ideal generative process. The third term accounts for the fact that we only train on a limited sample of data and do not train the model to full convergence. Theoretically, as both n and d approach infinity, a large language model should get closer to the irreducible loss E of the underlying text distribution. Given a compute budget C, where the floating point operations for n and d equal C, we can express the optimal number of parameters as proportional to C raised to some exponent A, and the optimal dataset size as proportional to C raised to another exponent B. Experiments have shown that these exponents are approximately 0.49 for A and 0.5 for B. This leads us to the main idea: we need to scale the number of tokens in proportion to the model size. However, as we discuss later, the availability of high-quality tokens is a growing challenge in pre-training, prompting us to explore alternative training methods and architectures. Recent studies indicate that many modeling and optimization techniques simply shift the error without fundamentally altering the power law exponent. We also discuss the two-simplicial transformer, which extends the dot product attention from bilinear to trilinear forms. In a standard transformer, given a sequence X, we have three projection matrices, W_Q, W_K, and W_V, which we use to derive the query, key, and value. The attention logits are calculated as the dot product of the query and key vectors, normalized by the square root of the dimension. These logits are then converted into probability weights using a softmax operation. The final output of the attention layer is a linear combination of the values based on these attention scores. In the two-simplicial transformer, we introduce two additional projection matrices, W_K and W_V, which allow us to compute new key and value vectors. The attention logits are then derived from a trilinear product involving the query, key, and the new key, resulting in a third-order tensor. The final output of the attention operation is defined using the element-wise Hadamard product between two vectors. We provide pseudocode for the two-simplicial attention, noting that this formulation does not include any position encoding, which we will address in the next section. Section Summary. In this section, we outline the notation used in our work, including how we represent vectors, matrices, and tensors, as well as key operations like dot products and matrix multiplications. We also provide an overview of neural scaling laws, emphasizing that the loss in large language models decreases as a power law with respect to model parameters and dataset size, and introduce the two-simplicial transformer, which extends the attention mechanism to trilinear forms for improved performance. Section: Determinant-based trilinear forms. In this section, we discuss rope, which was introduced to capture positional information in sequences for transformer language models. Rope applies a position-dependent rotation to the queries and keys, allowing the dot product of these elements to depend on their relative distance. Importantly, this dot product remains unchanged under orthogonal transformations, which is crucial for rope. When a query and key are at the same position, their dot product should not change with position-based rotations. We note that the trilinear form we defined is not invariant to rotation, meaning that applying the same rotation to the query and keys alters their inner product. To extend rope to 2 simplicial attention, we need to explore alternative bilinear and trilinear forms that are rotation invariant. We recognize that certain functions, like those described by the Saris rule, are invariant to rotations. Here, we define a bilinear form for 2-dimensional vectors and a trilinear form for 3-dimensional vectors. Geometrically, the absolute value of the bilinear form measures the area of the parallelogram formed by the 2 vectors, while the trilinear form measures the volume of the parallelotope formed by 3 vectors. We use the signed determinant operation to compute a specific matrix. For any vector, we can break it into chunks of size 3. The logits are defined based on the Saris rule, which requires us to modify our algorithm to use 2 ensembles instead of 1. We compute the final attention weights by applying a softmax function to these logits, similar to previous equations. For any input size, we can design a transformer architecture with a single attention head that produces specific outputs based on certain conditions. Since the sum of determinants trilinear function involves more terms than a simpler trilinear form, we will use the simpler form in our calculations for 2 simplicial attention without losing generality. Regarding model design, we note that 2 simplicial attention scales cubically with sequence length, making it impractical for long sequences. Instead, we parameterize it to scale linearly with a sliding window approach, where each query vector attends to a localized region of keys, reducing computational load. We evaluate different configurations to find the best balance between efficiency and performance. For causal dot product attention, the complexity for a sequence of length n involves 2 matrix multiplications, each requiring significant floating point operations. The causal mask allows us to skip half of these computations. In contrast, the complexity of 2 simplicial attention, parameterized by our window sizes, increases due to the additional multiplication required by the trilinear ensemble operation. We choose a window size that balances latency and quality, making the computational complexity of 2 simplicial attention comparable to dot product attention at a specific context length. A naive implementation of sliding window 2 simplicial attention would have each query vector attending to many different vectors, which could lead to inefficiencies. To address this, we adopt a model architecture inspired by native sparse attention, utilizing a high-grouped query attention ratio to ensure efficient computation without the need for costly masking. Section Summary. In this section, we explore the rotational position encoding, ROPE, for transformer models, emphasizing its position-dependent rotations that maintain dot product invariance for queries and keys. We also discuss the challenges of generalizing ROPE to 2 simplicial attention, propose alternative rotation invariant forms, and outline a computationally efficient model design that balances performance and complexity through localized attention windows. Section: Kernel Optimization. In this section, we introduce a series of kernel optimizations specifically designed for 2 simplical attention, building on flash attention with online softmax. For the trilinear operations, we use a method called 2D tiling, where we combine one input through element-wise multiplication and then perform matrix multiplication on the result. This technique allows us to efficiently overlap the computations of both the product of Q and K and the product of V and V' on different processing units. By implementing this in Triton, we achieve a performance of 520 teraflops, which is competitive with the fastest implementations available. We could potentially enhance performance further using a lower-level language like Cutlass for more precise tuning. However, we still achieve strong results compared to Cutlass for larger sequence lengths. For the backward pass, we face challenges due to the overhead from atomic operations when aggregating across 3 different dimension orderings. To address this, we split the backward pass into 2 separate kernels, one for calculating the derivatives of K and V, and another for the derivatives of K', V', and Q. Although this method adds some overhead from recomputing certain values, we find it preferable to the additional overhead from atomic operations required for a single combined kernel. We recognize that this might be a limitation of Triton's broader pipeline control, which makes it harder to manage atomic overhead. For smaller values of the second dimension, we adopt a two-stage method to compute the derivative of Q together with the derivatives of K' and V' without using atomic operations. We break down Q into smaller tiles along the sequence dimension. First, we process the even tiles, storing the necessary derivatives. Then, we handle the odd tiles, updating the stored derivatives accordingly. In our experiments, we train several mixture of experts, models, ranging from 1 billion to 3.5 billion active parameters. We implement interleaved sliding window 2 simplicial attention, where every fourth layer is a 2 simplicial attention layer. This arrangement helps balance the computational load during attention calculations, especially since both 2 simplicial and global attention are the most demanding operations in a single pipeline stage. We utilize the Atom W optimizer with a peak learning rate of 4 thousandths and a weight decay of 0.0125. Our training includes a warm-up period of 4,000 steps, followed by a cosine decay schedule that reduces the learning rate to 1/100th of the peak rate. We evaluate our models using benchmarks that test mathematical reasoning and coding skills, such as GSM-8K, MMLU, and MBPP. We observe that the reduction in negative log likelihood improves as we increase from a 1 billion to a 3.5 billion active parameter model. However, for models with fewer than 2 billion active parameters, we do not see benefits from using 2 simplicial attention. From our results, we can estimate how the scaling laws for 2 simplicial attention differ from those of dot product attention. Since we train both model types on the same number of tokens, we can simplify our loss expression. We find that the loss can be represented in terms of 2 parameters, alpha and beta, which we estimate from our results. We see that 2 simplicial attention exhibits a steeper scaling law compared to dot product attention, indicating a more significant performance advantage as model size increases. Section Summary. In this section, we introduce optimized kernel techniques for 2 simplicial attention, achieving competitive performance with 520 teraflops using Triton, and we address backward pass inefficiencies by decomposing it into 2 kernels to reduce atomic operation overhead. We also report on training various MO models, demonstrating that larger models benefit from 2 simplicial attention, which exhibits a steeper scaling law compared to traditional dot product attention. Section Discussion. In this section, we discuss how 2 simplicial attention enhances the scaling laws, but we should note that this method may be more beneficial when token efficiency is crucial. Our Triton kernel is effective for prototyping, yet it is not ready for production use. We need to focus on further developing the implementation of 2 simplicial attention to better suit specific hardware accelerators in the future.